if you look at the liquid meniscus, it looks nothing like a quadratic or cubic. It looks more like an asymptotic function, and you can make an exponential function look like an asymptotic. So again, D will be the correct choice. Hello everyone. So in this video, I'm going to talk about the water tank problem that appeared in the recent NEET paper. This problem caused a lot of pain for the students, but this is a really interesting problem. We get to learn a lot. I'm going to show you many different ways to solve this problem. We'll try to use a hack to solve it quick. We'll also use some formula to solve this problem, and then I'll show you different ways how we can solve this using the first principle. So along the way, actually, I will also ask you some questions. If you feel like those are stupid questions, actually, you're doing great. Your fundamentals are strong. But if you're struggling with that questions, please take a moment to think about it. And if you cannot seem to figure it out, please let me know and I'll try to help. All right, so let's get started. All right, so basically I have a water tank. There is a wall at x is equal to L, and the water has surface tension S and density rho. And because of the capillary action, the liquid meniscus makes an angle theta 0 with the wall at x is equal to L. All right, and the theta 0 is given to be very small. And we need to find out the equation for yx. Basically, we need to find the shape of the meniscus. All right. So at the wall, it makes angle theta 0. And as you can imagine, far away from the wall, the surface is going to be flat and theta is going to be 0, right? And then theta will slowly start increasing and it will be maximum at the wall. So anywhere in between, theta is going to be even less than theta 0. That means we can use the small angle approximation, which is theta is equal to approximately sine theta, which is approximately equal to tan theta, and which is dy over dx. Whenever I see a physics problem like this, the first thing I do is try to check three things. First is unit or dimension. Second is limit. Third is symmetry. All right. So in this case, if you look at the choices, they are all dimensionally correct. So we are out of luck with this. Next, let's check limit, meaning in the limit, when a parameter is very large or very small or equal to something, does it make sense? All right, so let's take a look at the choices. So this tells me the slope is a linear function of x. So let me actually make a plot here. So this is x, this is dy over dx, and this is a linear function. So this is choice A. When x is equal to 0, the slope is 0, which kind of makes sense. Far away from the wall, where x is 0, the surface is flat, so the slope will be 0. All right. Now choice B. So if I integrate it with respect to x, so this will be again a linear function of x, and then when x is equal to 0, slope will be 0, so the integration constant will be 0. So this will be exactly same as this line. So this is both choice A and B. Here, if I integrate it with respect to x, this will be x squared by 2. And the integration constant will be again 0, because far away from the wall, when x is equal to 0, the slope has to be 0. Right? So this will be a parabola, something like this. Right? So this is choice C. Now, this is not that straightforward to integrate, so we'll get back to that later. Now, think about how the liquid surface should look like. Let me draw a tank. It should be flat, far away from the wall, and then near the wall, because of capillary action, it rises up. Now, according to this, the slope keeps increasing linearly or quadratically. That doesn't make sense, right? Far away from the wall, it is going to be mostly flat. Slope will be 0 all the way, and very close to the wall, it will keep increasing. There is one thing. The second thing is, this tells me that the slope will keep increasing indefinitely with increasing x, but that contradicts what is given. The maximum slope near the wall is going to be less than 1, so it cannot keep increasing indefinitely. And the third thing is, let's say this is my wall, x is equal to L. So this curve tell me that the theta 0 is going to be smaller for a smaller tank and bigger for a bigger tank. That also makes no sense. If I have a larger tank, it will be still flat, and only near the wall it will keep increasing like this. And this near the wall should look exactly the same. Far away from the wall, it will be flat, right? So again, these three choices make absolutely no sense. Then D must be the correct choice. Here, the argument was based on the slope, but we can also argue in terms of the shape of the liquid meniscus. In the choice A, y will be a quadratic function of x. For B, y will be again a quadratic function of x. For C, y will be a cubic function of x. And choice D, y will be an exponential function of x. Now, if you look at the liquid meniscus, it looks nothing like a quadratic or cubic. It looks more like an asymptotic function. And you can make an exponential function look like an asymptotic. So again, D will be the correct choice. Okay, I have a couple of questions here for you. Now, in this problem, we assume that theta naught is much less than 1. So, is this analysis going to work if theta naught is 1 degree? You have to explain why. And the second question is, for small theta, we can make this approximation, theta is equal to dy over dx. So let's say we compute a numerical value of dy over dx. Let's say dy is 0.01 and dx is, let's say, 1. So this value that I get, is that going to be in degree or radian? Please let me know. Before we move on, I wanted to make a quick note. I had to explain this to you. That's why it took me several minutes. But once you become expert in doing this kind of analysis, you'll just look at the choices and then it will take you seconds. All right. I know that some of you are probably dying to know how to solve this so that we can get the exact shape of the meniscus. So I have that for you in the next slide. Okay, so we are going to solve this equation with this boundary condition, theta is equal to theta naught and x is equal to L. Just as a side note, try to contrast this with the simple harmonic motion. But moving on, we assume a general form of the equation like so. This term is actually going to be negligible, and then we take the first derivative and then second derivative and then try to equate this with this. Then I get the value of beta, and then we apply the boundary condition and we get the value of the constant C1, put everything together, and we get this for the shape of the meniscus. I've taken this for water and silicon, where theta naught is 0.5, and then plotted the shape of the meniscus. And as you can see, it is flat all the way, and at wall, which is at L is equal to 1, it rises up, right? And also notice the scale here. Now, just to get a better view of this area, I took beta is equal to 2, and for two different sizes of the tank, one smaller and bigger, I plotted the same thing. And as you can see here, the shape looks exactly the same. That is what we had assumed there, right? And before I forget, actually, there is a question for you. How can I neglect this term? All right, now let's look at the second method where we are going to use some formulas. Okay, let's think about the physics for a moment. We know that surface tension along with the adhesive force, it gives rise to the liquid meniscus, which has a curvature that is given by this formula. And the curvature in turn gives rise to a pressure difference that is given by this formula. Here R1 and R2 are the radius into principal axis. Now, we also know that for a liquid, the pressure difference also somehow depends on rho g. So if we can find the exact formula for the delta P in terms of the rho g, I'm all set, because that relates to radius of curvature, which relates to the first and second derivative, and that's what I'm looking for. All right, so there are a couple of things that is not explicitly stated in the problem, but it's kind of understood, and that is far away from the wall, the liquid surface is going to be flat, and we consider that to be y is equal to 0, and then measure y with respect to that flat surface. So this will be my y. All right, so with that, let's try to figure out what will be this pressure difference. We know that pressure is going to be atmospheric pressure here and here, everywhere on the top, right? Now, what will be the pressure just below the surface here? Now, the pressure difference here is going to be, because it's a flat surface, the radius of curvature is going to be infinite. So the pressure difference is going to be 0. So the pressure here will be the same as pressure just below the meniscus there, because it's flat. Now, if I go along this horizontally, I know that since the liquid is stationary, the pressure has to be the same. So the pressure here also will be P naught. That is at this point, right? So then what will be the pressure just below the meniscus? Let me call this P dash. So the P dash is going to be whatever the pressure plus the pressure due to the liquid column, which is rho gy. So this pressure plus the pressure due to the liquid column, right? So this will be plus. So this should be P naught. That should be P naught. That means P dash is going to be P naught minus rho gy. Then the pressure difference between top of the above the meniscus and below the meniscus, so that is the delta P. So that is delta P is going to be P0 minus below the meniscus it is P dash. So P0 minus P dash is simply going to be rho gy. All right, now we are all set. Here delta P is rho gy. This is going to be equal to surface tension times 1 over the radius of curvature. I'll get back to that, plus 1 over the other radius of curvature. So if you look at the liquid meniscus, let me see if I can find a paper. Okay, let's consider this is the liquid meniscus. So it is something like this. So this will be one radius of curvature. The other radius of curvature will be this, but this will be a straight line. So the radius of curvature is infinite. So this is going to be infinite. Now what will be this radius of curvature? That we can get it from here. It is given in the problem that the slope dy over dx is very small, it's negligible compared to 1. The whole numerator is going to be 1. So it's going to be 1 over, this one here is d square y over dx square. Now this is 0. If I rearrange it, this comes to the top, so that is d square y over dx square. S comes this way, that is rho g over s and then y, and this is exactly this one, right? So we get the same answer. All right, so here also I have a couple of questions for you. Why is the radius of curvature infinite for a flat surface? Can you explain it using this equation? And the second question is, for a flat horizontal surface, the radius of curvature is infinite. But what about with a flat but inclined surface? Is the radius of curvature still going to be infinite? Let me know. Next, I'll show you how to solve this problem using the first principle. It actually boils down to choosing an element and balancing the forces on it. So if I choose a differential surface element and balance the force in the vertical and horizontal direction, I get these two methods. Then if I choose a differential column element and then balance the forces, then I'll get these two methods. And then if I choose an extended element and then balance the forces, then I'll get these two methods. We'll talk about that next. In the first example, I'm going to choose a differential surface element between x and x plus dx, and I'm going to balance the vertical forces on it. I have drawn a bigger picture here. Let's first try to figure out what are the forces acting on it. So we have a surface tension S at an angle theta, and at x plus dx, the same surface tension at theta plus d theta. And then pressure on the top is atmospheric pressure. Pressure on the bottom of the surface element is P naught minus rho gy. We already figured that out in the previous method. All right, now I'm going to write down the forces. Let's first the forces in the upward direction, that is S sine theta plus d theta times L. L because S is force per unit length, so I'm taking an arbitrary length L in this direction. And then the upward force due to this, that is going to be P naught rho gy times the projection of the surface in this direction, right? That is dx times L. And then, so that is the upward forces. The downward forces will be S sine theta. And then due to this atmospheric pressure, that is going to be P0 x dl. Then I use the small theta approximation. So basically, I just get rid of this sign, right? And then if you look at it, I can cancel this with this, and then this theta will cancel with this. What is remaining is S d theta is equal to rho gy dx. Okay, and then I just do rearrangement. That is d theta by dx will be this, and then I substitute for theta, and then I get the result which is same as before. All right. Now here I have a couple of questions for you. Now if dx is very small, then this surface element, so this will be a straight line. In that case, this angle and this angle should be the same. Then why am I taking here as theta and here as theta plus d theta? Let me know. The other question is, at this point, the coordinates are x plus dx and then y plus dy, and then the angle is theta plus d theta. Then why not s plus ds, and why simply s? Please let me know. All right. The next method is I have the same surface element, but right now instead of the vertical direction, I'm balancing the force in the horizontal direction. I have the steps here. I'll spare you the details. Please go through it and let me know if there are any questions, but we end up with the same result. Let me ask you those questions though. Now, the pressure above the meniscus, right, is atmospheric pressure and is going to be constant. So that makes sense. But the pressure underneath the liquid meniscus, it depends on the height. Height here is y. So the pressure here should be P0 minus rho gy. But at this point, it should be P0 minus rho gy plus dy, right? So how can I assume the pressure to be uniform along this, as I have assumed here, right? I'm assuming the pressure to be uniform, so how can I do so? Please let me know. All right. In the next method, so instead of just choosing the surface element, I'm picking the liquid column that is below that surface element and above y is equal to 0. I've drawn a bigger picture here. Now, the forces here are like the surface tension. Okay, let's first look at the vertical one. The surface tension here, right? And in the vertical direction, there will be atmospheric pressure here. And then there is pressure here at y is equal to 0. Y is equal to 0 is P naught. We already figured that out. And then mass of this element, right? And the mass will be given as like density times the volume. Volume is dx times y and L. So this is the volume, right? And once you do this, actually, you will see that the force balance is exactly same as the earlier method 3, where we were considering just a surface element and balancing the force in the vertical direction. So of course we are going to get the same answer. All right, so here the question is, if you take a look at how I'm computing the mass, I'm taking dx y L, so dx, and this is y and L. So I'm basically considering the mass of this. So why am I neglecting the mass of this elements? So please let me know. All right, again, let's move on. It's the same, column element. So in this case, I'm balancing the force in the horizontal direction. Again, I'm not going to go through the details. Let me know if there are any questions, but this will, will be same as the method 4, where we were considering a surface element and balancing the force in the horizontal direction. It will be exactly the same. So we will arrive at the same answer, of course. Okay, the question here is, now, in this case, so I need the pressure at this point here. At that point, shouldn't the pressure be, rho g y plus dy by 2, because until here it is y and this is dy, so middle point of that will be dy by 2. So shouldn't the pressure be this instead of this? Let me know. All right. So next is, I'm considering this extended element. So from, where the surface is flat all the way to some arbitrary location, let's say x. So in this case, okay, what are the forces? So I have the surface tensions in this direction, surface tension here, and then the pressure here and pressure below, right? And then the mass of this element. Let's first do the vertical equilibrium. So let's first look at the forces in the upward direction. That is going to be S sine theta. That's what is this. And in the vertical direction, it is going to be, this is the pressure times the area is going to be, this distance is x times the L. So that is this. So that should balance with the weight. So that is the mass times the G. And then the pressure downward is going to be again this P0, and the projected area is x time L. This cancels out, and then I get to this, and then with some simplification, let me know if there are any questions, but again we get at the same answer. All right, the last method here, in this case I have the same element, but now I'm balancing the force in the horizontal direction. So let me go through it a little bit. So in the horizontal direction, so I have the on the forces to the left, so that is surface tension times length, and then the pressure here, which is P0 minus rho g. I take the pressure at the center times the area. So pressure at the center is this times the area. So this is the force to the left. Force to the right is going to be this surface tension cosine theta here, and then because of this pressure times the projected area in this direction. So P0 and then YL, that is the projected area, right? Okay, once I do some cleanup here, I get to this expression, and then I make an approximation for cosine theta. So cosine theta is basically cosine 2 times theta by 2. Then cosine 2 theta is cosine square theta minus sine square theta. I'm making that approximation here. Then for small theta, I'm assuming this to be 1, and this is basically going to be theta by 2 square, right? I'm making that approximation there. So with some simplification, I get to this point here, and that this gives me this equation. Now this actually does not match with the previous. I get an extra 2 here. I have made some mistake. I want you to figure out where I went wrong here. All right, so that is actually one of my question here. The other question is, why not just make the small theta approximations right here and assume cos theta is equal to 1? Please let me know. All right, so that kind of summarizes the all the methods using the first principle. So as you can see, we are choosing an element and balancing the forces. That's about it. You just need to do it different ways to get some practice. All right, that kind of concludes everything I had to say about this problem. But what was the purpose of making this video? It was less about showing you the answer. It was more about showing you the different paths, how to get to the answer. That's more important. So hopefully, I got that message across. It was also about making you aware that tough problems can have a very simple hack, right? That comes with practice. It was also about asking you stupid questions, because that will make your fundamentals very strong. All right. Finally, I just wanted to say that I'm starting to make videos for NEET and JEE, so your feedback will be extremely helpful for me. And if you want to teach physics with me, please let me know. Please get in touch with me in LinkedIn. So thank you very much. I'll see you in the next video.